Welcome to the next lecture of signals and systems. Now in this lecture we will talk about the next topic, which is discrete time Fourier transform. So this is the last topic of this unit. Now in this unit we talked about the Fourier series, that is the continuous time Fourier series as well as discrete time Fourier series. Then we talked about the continuous time Fourier transform, and now this is discrete time Fourier transform. So as the continuous time Fourier transform is usually evaluated for continuous time signals which are aperiodic, similarly the discrete time Fourier transform will be evaluated obviously for discrete time signals. Okay, so now the discrete time Fourier transform of any signal xn, it can be represented or it can be evaluated by using this mathematical expression, that is summation n equals to minus infinity to infinity xn e raised to the power minus j omega n, where this is the discrete time signal whose Fourier transform have to be carried out, or it is to be evaluated. So this is the expression for discrete time Fourier transform, and similarly the inverse Fourier transform can also be found out by using this expression. So this is usually for inverse discrete time Fourier transform. Okay, so this signal x of e j omega, it can also be represented or it in the way that x of g omega is representing actually the discrete time Fourier transform of xn. Okay, so this can also be written in this form. Similarly, for inverse Fourier transform, we can write that xn representing the inverse discrete time Fourier transform of x e raised to the power j omega, or sometimes it can also be represented as this. Okay, so this f inverse is usually representing the inverse transform. So these are the two expressions which we generally use in finding out the Fourier transform or inverse Fourier transform of the given signal. So symbolically, as we did for the continuous time Fourier transform, we can also use this kind of notation for the discrete time Fourier transform. So this is any given signal, any discrete time signal, and this is representing its discrete time Fourier transform. So generally this Fourier transform, which is x e raised to the power j omega, this is a complex function. Okay, so complex function of this variable omega. So we can also represent it in the rectangular form. So we may write it as the summation of the real and the complex part. So this is representing the real part and let's suppose that this is representing the imaginary part. If we write it into the rectangular form, so this is representing the real part and this is representing the imaginary part of this overall signal x e j omega. Okay, so you can also find out the expression of xr. If you want to write xr e j omega, you can just obtain it as x e j omega plus x conjugate e j omega. Okay, so obviously this conjugate is denoting the complex conjugate of this signal x j omega, and similarly for the imaginary component you can obtain the similar type of expression with a negative sign in between. Okay, so the Fourier transform actually it can be expressed in one more alternative form, that is, this is representing the magnitude along with an angle component. Now where this theta omega is actually representing the angle component here. Okay, so this actually magnitude part which is being shown here, so this is called the magnitude spectrum, and the quantity theta omega, which is equal to the angle part of this will be called the phase spectrum. Okay, so if in any problem it has been asked to evaluate or to find out the or to draw the magnitude and the phase spectrum, then you have to proceed in this manner. Now let's suppose we try to solve one problem. The given signal xn equals to a raised to the power n un, where this a is having the magnitude of less than 1. Okay, so the question is that you have to find the Fourier transform for this signal. So obviously this is a discrete signal, so discrete time Fourier transform we'll try to find out. So x of e j omega, we'll just write the same relation which was explained in the first slide, xn e raised to the power minus j omega n, and now you try to put the given signal in this expression. So this is a raised to the power n un e raised to the power minus j omega n. So this will be from n equals to 0 to infinity a raised to the power n e raised to the power minus j omega n. So since this is un which is being attached here, so the limit is being changed to 0 to infinity. So this x e j omega will be equal to a e minus j omega times n, or it can be written as 1 over 1 minus a e raised to the power minus j omega. So what you get from here, that the Fourier transform of this given signal a raised to the power n un is 1 over 1 minus e power minus j omega, with a having the magnitude less than 1. Okay, now if you also have to plot the magnitude and phase spectrum for it, then how will you proceed? Let's see. So first you have to just multiply the numerator and denominator of this obtained expression for the Fourier transform by the complex conjugate of the denominator. So let's see, we'll try to do that. So after multiplying both the numerator and denominator by the complex conjugate, so you will get this expression. Okay, so 1 minus a cos omega minus j times a sin omega upon 1 minus 2a cos omega plus a square. Now this expression can be divided into the real and the imaginary parts. So we'll try to write them separately, the real and the imaginary parts. So what will be the real part of it? That will be 1 minus a cos omega over 1 minus 2a cos omega plus a square, and the imaginary part will be minus of a sin omega over 1 minus 2a cos omega plus a square. Okay, so now this is the real part, this is the imaginary part. Now you can obtain the magnitude spectrum by using both these real and the imaginary parts. Okay, so in this manner you can get it. So when you just put the values of the real and the imaginary part in this expression, you will get 1 over under root 1 minus 2a cos of omega plus a square. And similarly the phase spectrum which you will get will be equal to tan inverse of imaginary part over real part. So again that will be equal to tan inverse of a sin omega over 1 minus a cos omega. So this is the expression for the magnitude and phase of this Fourier transform. Now for different values of a, the plot of the both these magnitude as well as phase spectrum will be different. So let's suppose that uh, first I will try to plot it for the values of a in between 0 and 1. So you can also try to plot it some kind of this plot you will get. Okay, so something like this you will get. So this is the magnitude spectrum. Okay, some minimum and maximum values will be there. This is pi, this is 2 pi, similarly this will be minus pi, this will be 2 pi, and similarly the phase spectrum will be something like this. Okay, so again you just try to draw the exact. I'm just trying to draw it accurately. So this will be the phase spectrum. Now both this magnitude and phase spectrum which are being shown here, this is for values of a in between 0 and 1. Okay, so something like this waveform you will get. You can just correct this a little bit, something like this it will be. Okay, so similarly for the values of a in between -1 and 0, the curve will be different. Okay, so whatever maximum point you are seeing here, so in this range this curve will be somewhat different. So you can just try to plot it for this value. Next we'll try to solve one more problem. Now the given signal is xn a raised to the power n u of minus n minus 1, where this a is greater than 1. So again you can just start by writing the expression for the Fourier transform. Summation n equals to minus infinity to infinity xn e raised to the power minus j omega n and then you put the signal which is given to you. Okay, so obviously the limits will be modified according to this unit step signal which is given to you. So this can be written as n equals to minus infinity up to minus 1 . So you can just see that if this is u of minus n minus 1, so obviously the limit will be up to minus 1. You can just see it, we have done it so many times now. So now you just have to solve this summation Now here a change of variable can be performed by just assuming that m equals to n minus 1, which will give you n equals to m plus 1. Okay, so you can see here that m equals to 0 as n equals to 1 and m equals to infinity as n equals to infinity. So if you write the expression now after this change of variables, so you will get here m equals to 0 to infinity 1 upon a e raised to the power j omega m plus 1, which will be equal to 1 upon e raised to the power j omega summation m equals to 0 to infinity 1 upon a e raised to the power j omega m. This can be further solved. So just simplify the obtained expression. One upon a e to the power j omega over 1 minus 1 upon a e raised to the power j omega. So this can be simplified to 1 over so now we can write it as in the standard notation that the given signal in the problem has the Fourier transform of 1 over a e raised to the power minus j omega minus 1, where the magnitude of a is greater than 1. Now one more similar kind of problem we'll try. Xn equals to a raised to the power minus n u of minus n minus 1, where the magnitude of a is less than 1. So again you just start by writing down the expressions for Fourier transform. And then put the values here, that is whatever signal is given to you in the problem, put in place of xn. So obviously the limits will be modified according to the unit step signal which is given to you. So this will be I'm sorry, this will be minus infinity to minus 1 a raised to the power minus n e raised to the power minus j omega n a e raised to the power j omega times n. So again, as we done in the last problem, we can change the variables here. So just assume that if m is equals to n minus 1, okay, so again this n will be equal to m plus 1. So m equals to 0 as n equals to 1 and m equals to infinite as n equals to infinite. So therefore we can write the Fourier transform x of ej omega in terms of limits consisting of m0 to infinite a e raised to the power j omega m plus 1. So a e raised to the power j omega summation m equals to 0 to infinite a e raised to the power j omega common power m, which can further be simplified to this. Okay, so we can write down that this given signal, which is a raised to the power minus n u of minus n minus 1, will have the Fourier transform of a e raised to the power j omega over 1 minus a e raised to the power j omega, with the condition that mod a is less than 1. So this is how problems related to the discrete time Fourier transform are solved. The properties of the discrete time Fourier transform are more or less similar to what we have discussed in the continuous time Fourier transform case. There may be slight modifications, but more or less it will be same. So with this much we stop today, and with this much we have come towards the end of this unit, that is unit 3. From next lecture we'll try to discuss the next topic. Thank you very much.